All right, let's go over some of the notes here from Force and Motion. And as we first dive into force and motion, I think it's extremely important to understand what force is. As you're going through the Nearpod, I definitely think that this is a video to watch. It is a fantastic overview of the basics of force and motion. They give unbelievably detailed, for kids at least, detailed examples of friction, force, motion, inertia, gravity. They talk about it all, of the things that we're going to talk about in class, but they summarize it in a fantastic little small cartoon. It's about maybe 8 minutes long, I think, or something like that. It's a great video. Highly recommend watching that. But when we're talking about forces, we need to understand that forces are all around us. There are pushes and pulls going on pretty much everywhere. In class, we are pushing our pencil down on the piece of paper with a certain amount of pressure. We are pulling it across the paper, creating letters, which the letters create words, and the words are our notes that we're taking on force and motion. Anytime you have a car going by you, there's a plethora of forces and motions at work in there that are making that car move. When the wind is blowing, the blood pumping through your body, the food being moved through your body, being pushed through your body by peristalsis is force. All of those things are force, and it's important for us to understand that. And so when we define force, force is a push or a pull. Looking at the definition that we have, I probably need to go back and actually change that. A push or a pull exerted by one object on another is absolutely correct. Causing a change in motion, not necessarily. I can walk up to the school and apply force to the wall by pushing on it. And I'm going to go ahead and let you know right now, there's no motion. I'm not moving the wall. I don't have enough force to do that. So it doesn't necessarily mean that there's always a change in motion. And that generally when we're talking, there might be a change in motion, though. So that's something to think about. Some forces act when things touch. Example, like when your foot touches the football and you are kicking the football into the air, that is a force. And that's when two things are touching. Sometimes forces act over a distance. For example, when there's no touching involved at all, that ball that we kick in the air is not going to stay there. It is going to be pulled back down toward the earth by a force we know as gravity. So forces can be things touching. It can be things that are not being touched, but it is most definitely a push or a pull exerted on one object by another object. Skip over that. You're welcome to do these when you're working. Here's another fantastic video on force and motion that wraps up everything in a theme park. And a theme park is an unbelievably great place to go for forces and motion. As a matter of fact, Carowinds has an entire forces and motion physics day that they allow students to come down for. I don't think that we'll ever get to do that as a field trip. Maybe I could try that one year. I think that'd be a lot of fun. But definitely watch this video, take you some notes on that one as well. Gravity. If we take the little yellow frisbee outside and we throw it, if we throw a ball, I know that Malachi and Will have been playing with this like little catchers and this like wiffle ball every day, and I watch them throw the ball way up into the sky, but the ball always seems to fall back down. Well, there's a reason why that. Gravity. Gravity is a force that pulls things towards another. And we typically talk about how when we drop something on Earth, the Earth pulls it towards the Earth. Were we on another planet, gravity would be pulling it towards that as well, depending on how much gravity could be pulled down faster or a lot slower than it is here on Earth. And I don't think we're able to study that too deeply, but we'll see how that goes. When we jump, so for this person here, our legs push us up off the ground. We have to have enough force to overcome the gravity in order to get us up off the ground, and most of us have enough energy to get up off the ground a little bit, but we do not have enough energy in our legs to push us far away from Earth that we overcome gravity completely. We are always pulled back down when we're jumping by gravity. That's why rockets have to have so much power to get out of the atmosphere of Earth, is because they're spending a lot of their time overcoming gravity. This is a great video on friction. I'm going to be very honest with you. She gets very mathematically detailed about friction in some of the instances in there. You do not have to worry quite so much about all of that. Just know that it's a great video to watch to give you an understanding, because they show you that even smooth things still have tiny little bumps on them. And even if we're rolling like a bowling ball on the floor in the classroom, both of those are very slick. There still is a slight amount of friction occurring between those two. And I know that here in a few minutes we're going to look at some things where there's like very little friction, but there still is friction because two things are rubbing against each other. When two forces, I have got to go back in and change that today. That is the next thing I'm doing. When two objects slide against each other, a force called friction makes them stick together. Depending on the two objects, they either don't stick together very well at all. We'll look at that in just a moment, or they stick together very well, and we'll look at that in just a few moments. Typically, friction is one of those things that slows things down. Think about it like this. When I roll a soccer ball across the field outside on the playground, the soccer ball is hitting the grass, and the friction between the ball and the grass is what causes the ball to slow down. Here's an example of friction, ice skates and ice, and this is an example of very little friction. Now, even if this person were to push off on the ice and start moving, if they did not put any more force on it, they would eventually come to a stop. Now, obviously, if that same person were on pavement, they could push that with the same amount of force, and they're not going to move hardly at all because there's too much friction between the skate and the pavement. There's very little friction between the skate and the ice. So it depends on the two surfaces that are rubbing against each other to determine how high of an amount of friction we have. In this one, we started talking about Goldilocks and the Three Bears, and we said, when Goldilocks went to the house, some of the porridge was too cold, some of it was too hot, and some of it was just right. When we're looking at friction, if there's Goldilocks, this is too little friction, although sometimes that is a good thing. I would say that this is just right. She has on the proper boots to be walking in gravel like that. They're going to give you just the right amount of friction. Imagine being in the school and you're trying to run up and down the hall in socks. You know that when you try to come to a stop, you're going to slide because there's not a good amount of friction between you and your feet. If you're wearing shoes, you are doing a fantastic job. You have just the right amount of friction. Now, if you happen to be wearing like shoes that were made out of like inside out duct tape or something, and they were very sticky, then all of a sudden there's too much friction and it's harder for you to move and run, and you don't want that, because friction is one of those things when two objects are rubbing against each other, and typically sometimes friction can cause things to slow down. Looking at this train versus this train. I know that for a fact, I asked everybody in class this, which one of those trains, if I had a case of $1 million and said you had to drag one of these two trains or push one of these two trains 100 feet, which one would you pick? Everyone picked the toy train, and they said, well, because it's lighter. You're just about there. We just have to add in a new vocabulary word for this week. The reason why this train is so much harder to push or pull than this train does have a little bit to do with weight, but it's mostly has to do with mass. Mass is the amount of matter or stuff inside of an object. Now, it's very easy to look at those two trains and say, well, Mr. Bullens, I would rather push the toy train. Let's think about something that are roughly the same size. What about a ping pong ball and a golf ball? Or a baseball and a tennis ball? Those two things are about the same size, but they have very different masses. In a ping pong ball, very light. I could take a ping pong ball, put it in my hand, and thump it, and I could probably thump it across the classroom. If I pick up that same golf ball and thump it with the exact same amount of force that I thumped the ping pong ball with, I'm probably going to hurt my finger because the golf ball has more stuff, more matter on the inside of it. So now, I would expect you, when I'm describing how to push or pull something, you're no longer going to just talk about weight, because we need to think about this. We might weigh a certain amount here on Earth, but if we went to the moon, our weight would change. That has to do with how gravity is pulling on us. The thing that would not change from here to the moon is how much stuff is inside of us. That would not change. We would have the same mass on Earth as we do on the moon, but our weight would change because gravity is pulling on our mass differently on those two areas. That's a little tough to understand, and we'll keep going over that, but it's just the truth. Mass, the amount of matter inside of an object. Again, thinking about those trains, I grew up with two boys, like I've told the kids in class, and we played a lot of Thomas the Train when we were little. And we had a great time doing that. And I watched a lot of Thomas videos. And then one day we got tickets to Spencer, and we actually rode a giant, real, life-sized Thomas, which was pretty awesome. The big difference between those two, one, the little one, the toy train, I could carry around in my pocket all day because it didn't have a lot of mass. And it was there for when the kids got bored and they wanted to play. The big one takes a lot of energy to move it. And that brings us to the next thing about mass. The larger an object, the more mass it has, the harder it is to move it. I don't think that that's a difficult thing. You've already said it's easier to move the little train than it is the big train. That blends right into this. The more mass something has, the more force it takes to move it. The less mass something has, the less force it takes to move it. That's pretty simple. We just have never really put it in those terms. Now we're learning a little bit more about that. If we went outside to the playground on the little hill beside the, like where the other basketball court is, and we were to roll a small ball down the hill, or a small rock down the hill, I don't think we would have any issues doing that at all. It would be easy for me or you to pick up that rock. It would be easy to roll it down the hill, and it would honestly be very easy for the person at the bottom of the hill to stop that small rock from rolling. They could probably just stick their foot out, block the rock would stop, and they would move. Because it has little mass, it's very easy for for anybody to get the rock moving or to stop the rock. Not a big deal at all to do that. However, if we went outside with a giant boulder, it has a lot more mass. It would be very hard for any of us to get it to start rolling, and it would be extremely hard for someone to stop it. If Reagan happened to be at the bottom of the hill trying to stop that, it would flatten her. We don't want that. Again, that's a joke at the bottom. I don't take that serious. But again, it takes more force to stop an object that has more mass once it gets rolling. If we were to go outside and I rolled a toy car at you, you could probably stick your foot out and it would hit your foot and not a big deal. If we drove a real car at you and you stuck your foot out, you're not going to stop the car. It's going to run you over because it has more mass. It all boils down to mass. And it's easier to move small things with little mass, and it's harder to move things with big mass. It's easier to stop things with little mass. It's harder to stop things with more mass once they get moving. And that is really the crux of mass, and we'll talk about that even more as we start to get into some more of the... I am going to stop there for this video because the next thing that we're going to get into is we're going to start talking about the 3 laws of Isaac Newton, which literally have to do with inertia and mass and things that happen with force. And they're very easy if you can understand all of the terms that we're throwing at you very quickly. Don't forget to be studying for your vocabulary, as we are going to have that vocabulary quiz on Friday. And as always, don't forget to smash that like button and subscribe to the YouTube channel.